Good evening and welcome everybody. This is Obi-Wan Piz for N-Simplex Pachinko, and we're doing math stuff tonight, so if anybody has any questions, let me know. We are attempting to, as said earlier, raise money for GOtEL. That is Game On to End Lupus, although tonight, I suppose, we're doing some Motel Math On to End Lupus. The three people running the event are, again, 8-Bit D, Coco Confession, and L Bell, who are friends of the channel. GOtEL. And if you want to pop into their channel, say hi, and donate through them, that's perfectly fine. I just have some interesting little rewards for anybody who might want to punish me for doing this. But it's all right. We'll keep running charity events every so often. Also seen in GOtEL, there are approximately 160 streamers who are running some sort of campaign with some sort of goal. Again, ours is $250. I figured that was a modest sum. Might even be too far from my reach, but that's all right. And also seen one of the other streamers I definitely know are there are Moohoodles and Science. So Belint and Moo are both friends of the stream and members of TKF, the Knowledge Foundation. No, the Knowledge Fellowship. There we go. And if, again, if you want to go see what they're about, they're some pretty awesome people. So go check out. Moohoodles is an astrobiologist. Also does games and all sorts of stuff. Normally she does like SciComm as her first part of the stream, and then gaming as the second part. And Science streams. Cool. Is Belint and his wife Lita and their daughter Ilona, who is not quite 2, I don't think. And they have their new munchkin. I don't actually know his name now that I'm thinking about it. It's okay. They're probably gonna do some sort of reveal later when he is able to toddle on. Say hi himself. Anyway. So if anybody has any questions, let me know. I actually would like to figure out what this is all about. Norman Wildberger from University of New South Wales in Australia worked with computer scientist Dean Rubine on a paper that details how incredibly complex calculations regarding higher degree polynomial equations has been puzzling experts for nearly 200 years, says sciencealert.com. Wildberger and Rubin took a new approach to a problem which is based on the Catalan numbers. So Catalan numbers, just for everybody who is not completely aware. Sequence of natural numbers that occur in various counting problems. Named after Eugene Catalan. Yep. Let's pop this over to this side. Flashbang. So nth Catalan number can be expressed directly in terms of the central binomial coefficients. We're aware of that, or we're aware of those particular numbers. C sub n is equal to 1 over 1 n plus 1. Choose, or 2n choose n. So 2n factorial over 1 plus n plus 1 factorial times n factorial. So first Catalan numbers are going to be 1, 1, 2, 5, 14, 42, 132, 429, etc. Got that right there. The OEIS is the Online Encyclopedia of Integer Sequences. So if you ever find a sequence of numbers that you think doesn't exist, check OEIS and see if it exists there. If not, you might be able to make an entry. So in this particular case, it's looking at C5 is the number of non-crossing partitions that you can make within a, well, in this case we have a pentagon. And right, the lower set is the other 10 which do cross each other, which is not what we want. Catalan numbers are non-crossing. So make a regular polynomial on a sheet of paper and then try to figure out how to partition those 5 things into, or however many you've got, n things, into as many groups as you can, again, without overlapping, without crossing each other. So those will be Catalan. Okay, so these guys Wildberger and Rubin took a new approach to the problem, which is based on Catalan numbers. By extending the idea of Catalan numbers, researchers were able to demonstrate that they could be used as a basis for solving polynomial equations of any degree. Well, that's pretty big. Oops. Missed you. There we go. Alright, this is the one we're looking at right now. Ugh, please excuse the ridiculous ads. Innovation lies in the idea that if we want to solve higher equations, we should look for higher analogs of the Catalan numbers. So this looks like it's not going to be, probably not going to be all higher degree polynomials, but at least a large subset of them have just been solved now. Departure from traditional method like radical expressions, and instead use combinatorics. Alright. Okay, discovered a new mathematical structure called a geode, which ties the Catalan numbers, ties into the Catalan numbers, seems to act as a foundation for them. The geode could be the basis for many future studies and discoveries. As the approach is so different from what's gone before, there's the potential to rethink many ideas mathematicians have relied on for computer algorithms, way data is structured, and game theory. Might even have applications in biology. RNA molecule folding as one example. Core computation for much of applied mathematics. Opportunity for improving algorithms across wide range of areas. Well, that's pretty amazing. Okay. Yeah. And Nakia Jackson et al. Also published last year 5 or 10 new proofs for the Pythagorean theorem. That wasn't the same one, right? No, they were doing the law of sines, or redefining sine. Anyway. Catalan numbers, count the number of subdivisions of a polynomial, given number of triangles, quadrilaterals, pentagons, etc. type M, and show that the generating series solves the polynomial equation of a particular geometric form. Yeah. The solution is straightforwardly extended to solve general univariate polynomial equation. Oh. So, not restricted. Alright, geometric polynomial formula. This equation given here. With all of our t's being coefficients and alphas being our variable. For permitted nesting, unending, nth root calculations, why not a simpler ongoing sum that actually solves polynomials beyond degree 4? Has formal power series solution given here. Is there any restriction on these? Okay, power series solution to a polynomial equation is not a new idea. GOtEL Eisenstein found such a solution to x to the fifth plus x minus t equals 0. Simplest polynomial known not to have a general 0 expressible in radicals. Write down the general quintic solution and use it to recover Eisenstein's series for the Bring radical. Section 9. Discuss natural connections with series reversion. So going back to Lagrange, section 10. Central algebraic object we wish to emphasize is hyper-Catalan generating series S in an unbounded number of variables. This is connected with online encyclopedia of integer sequences in so many interesting ways. You Curious factorization involving S reveals the mysterious GOtEL array, which algebraically encodes the hyper-Catalan numbers. In section 11, we offer several compelling conjectures about this new remarkable algebraic object. Alright, combinatorial path, they started looking at it with Euler and Goldbach. Good company. Okay. Joseph Mott solves general polynomial equation using undetermined coefficients in a remarkable self-published book in 1855. What? 1882 journal article writing 29 terms of S that he uses to approximate roots. Joseph Man uses Lagrange series reversion to obtain general form for the hyper-Catalan coefficient C sub m. Exasperatingly, doesn't quite write altogether despite title of his short note. Okay, clarified 1910 by Van Ostrand. Absorbed into combinatorics literature by John Reardon, 1968. It's quite a gap there. Okay. Hyper-Catalan coefficient while studying behavior of roots when polynomial coefficients are perturbed. I mean, it seems to me like Joseph Mott kind of did it. Unless he only just did one. Counts non-crossing partitions of a cyclic graph, independently deriving a more general way. Hyper-Catalan numbers appear when he considers non-crossing partitions without singletons. Reproduces Cayley's 1890 array, describing it as coefficients of the expressions giving a series reversion. Okay. Introduced by Euler in 1751 to count subdivisions into n triangles of fixed planar convex n plus 2 gon for a natural number n with convention that c sub 0 is equal to 1. Fair enough. Right, for a 0, oh no, for a 2 gon, right, then there is exactly one way to count it. in that there is not a polygon there. That expression is a sub-multinomial. Sum of the factorial inputs in the denominator is one more than that of the numerator. Okay, Catalan sequence has the longest entry in OEIS, subject of 3 relatively recent books, as well as a numerous research articles. Okay, C4 equals 14, the 14 ways to subdivide a roofed hexagon into 4 triangles. C sub 4 equals 14 ways to, yeah. See how Catalan numbers relate to quadratic equations. Consider 1 minus alpha plus t alpha squared equals 0, which according to usual quadratic formula has the following roots. Applying Newton's binomial expansion to the minus sign solution reveals generating series of the Catalan numbers and as the formal power series solution given here. The result justifies the lovely identity. Okay, let's make this go over here for a minute. Go over here. Clear out all this other stuff. Let's also just clear this thing out because it annoys me. Okay. So we have this formula here, and we said that Catalan numbers relate to 1 minus alpha plus t alpha squared equals 0. Right, quadratic equation from here is going to tell us that again. This is that alpha is equal to negative b over 2a plus or minus square root b squared minus 4ac. Okay. Applying Newton's binomial expansion to the minus sign solution. Which is So this is what Newton has. At this point, he would say that this is going to be 1 minus this thing, parentheses x plus y to the r is equal to sum as k goes from 0 to infinity. R choose k, and they're fractions, lovely. R minus k times y to the k. Yep, there it is. Where also, right, R choose k is going to be equal to R minus 1, R minus 2 times dot 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 out 2. Let's not cramp myself way over in the corner here. R minus k plus 1. Or R minus parentheses k minus 1. You can go kind of either way on that. All divided by k factorial. So for this, the expansion on this particular one is going to be 1 half choose 0 times x to the 1 half times y to the 0 plus 1 half choose 1 x to the negative 1 half y to the first plus 1 half choose 2 x to the negative 3 halves y squared and so on and so forth, literally forever. Okay, equal to 2t 1 minus 1 half choose 0 is going to be 1 half choose 0 means we have a 0 factorial in the denominator and r and r minus 1. So this is going to be a 1 half times negative 1 half all over 1 x to the 1 half. Okay, then a minus 1 half choose 1 That's fun. So since k is 1, that means that we're going to get r minus 0. So it should just be r, which then means that this is just going to be 1/2 over 1 times x to the negative 1/2 times y minus 1/2 choose 2. It's going to be 2 minus 1, so that's r minus 1. So again, this is going to be 1/2 times negative 1/2. This time divided by 2 factorial is 2 times x to the negative 3/2 y squared, and minus just one more for our benefit here. This is going to be 1/2 choose 3. 3 minus 2 is 2, so r minus 2 is going to be in there as well this time. Oh. Ooh. So actually, that first one should have gotten us r plus 1. So, I mean, choose 0, it's going to be 1, right? That's the idea here. But is that going to work? So, let our trusty calculator go to math probability, NCR. Cool. We want 0.5, choose 0. Domain error. Psh. Alright, whatever. We're going to go to Wolfram. Zero 0.5. Choose 0. Results 1. Yep. Alright, cool. Just making sure. Oh man, in terms of line integrals and everything. Okay. So, yeah, another one here. It's going to be 1/2 times negative 1/2 times negative 3/2. Again, r minus 2 gets us a negative 2 plus 1/2, so negative 3/2. Divided by 3 factorial is going to be 6. X to the negative 5/2. Right, so this is r is a half minus k at this point. No, it's just 3. Okay. Right, that one's 0. Okay, the negative 1, the 1 at the beginning is not part of our actual series. This is 1 over 2t multiplied by 1 minus. X is 1. Minus 1/2 times 1 times y is negative 4t. Okay, minus. Negative is a positive. 1/4 divided by 2 is 1/8. X is 1. Y is negative 4t all squared is 16t squared. That's a plus. And then a minus 248 divided by 6 is going to be 48 times 3 up top is going to be 1/16 times 1 times negative 4t parentheses squared is going to be a negative plus 64 t cubed minus, and then it's going to go from there. This is going to be a 1 over 2t. 1 minus 1 is 0, so that's gone. A minus times negative 4t is going to make that a plus. 4 over 2 is 2t. Lovely. That's going to go away with the 2t out front. Just make a 1 as the first term. Next is 16 over 8 is 2 t squared. Next is 64 over 16 is 4 t cubed. And then it's going to go from there. Okay, so this is going to be a 1 plus t plus 2t squared plus, and then it's going to go on from there. So, what do they have? Nope, not that one. Where'd I put that? Did I close it? I didn't think I closed. Recently closed tabs. No. Full article, Hyper-Catalan series. Yeah, where's that? Oh. Yep. Never mind. That's over there. Alright, 1 plus t plus 2t squared plus 5t cubed plus 14t to the 4th plus 42t to the 5th, etc. Okay. So, that's going to... might as well adopt that, because yes, we got at least the first 3 terms. Okay, 5t cubed, 14t to the 4th, 42 to the 5th, plus dot dot dot. This is alpha. Okay, and then it said alpha squared is going to be, so now we can do this a little bit more ridiculous. This might not be the most efficient way to do it, but this is helpful to at least see it. Sloppiness indeed. Okay. 1t. Oh yeah. Need that there too. third, 14t to the fourth, 42t to the fifth. Alright, fill out the product. T. Alright, 2t squared. I already know what this is going to be too. Might as well fill that out while we're here. And then we also know what the next row is going to be as well. Okay, it's going to be 4 to the fourth, 10t to the fifth, 28t to the sixth, and 84t to the seventh. Next one, 5 times, it's going to be 10 t to the fifth, 25t to the sixth, 70, yep, t to the seventh, and 210 t to the eighth. Same deal, 28t to the sixth, 84t to the seventh, 70t to the seventh, and 210 t to the eighth. Okay, this is what is that, 286, 100, oh no, 186, 96, 196 to the eighth, and then 14 by 42, interesting, okay, so, another way to do that is multiply by 10 first to 420, nice. And 4 times that is going to be 168. So 168 plus 420 is going to be 588. T to the ninth. 42 squared is going to be 1764. T to the 10th. All like terms are on diagonals. So we can just go through and calculate those up. So we end up with 1 plus 2t plus 45t squared plus 10, 14 t to the third, 28, 38, 42. where did... 84, 104, 124, 132. Okay, 84, 56. It's going to be 140, 165. To the 6th. Times 2 is 168 plus 140. 168 and 140. 308. $420. 520 minus 4. 516. $1,100. 76. And 1764. Oops. We can't go any further than the one that is hitting the edge. T to the 5th. Because for the rest of these, we're missing all these other terms that are down here, and all these other terms that are out here, and all the terms that are out around the outside. So with all those terms missing, we can't actually do anything greater than t to the 5th. That's it. Plus dot dot dot. Okay, so the point here really was that we were trying to come up with something that is taking like the next Catalan number. It's basically taking the entire series of coefficients and shoving them down one. All right. Okay, this is getting way too complicated from this point on, but Uses Euler polytopes, sub-Diagon multisets, accounting monomial, sub-Diagon polyseries. These will solve general polynomial equations independent of any explicit counting formulas for C sub m. Jeez. C sub m is the hyper-Catalan number, which counts the numbers of sub-Diagons with M2 triangles, M3 quadrilaterals, M4 pentagons, etc. Then we multiply that by T2, which is our coefficient from the above polynomial, raised to the M2 power, times T3, the cubic coefficient, raised to the M3 power, times T4, raised to the M4 power, etc. Now give, with the same change of variable that we used in quadratic case, give the series solution to the general polynomial for polyseries equation. Please note again, coefficient of linear term has a minus sign.
Fill your day with good vibes. With Spotify Premium, you can set a non-stop soundtrack for the day ahead. Start 3 free months now and cancel anytime. Tap the banner to learn more.
The bi-tri array and a one-line cubic approximation. Give an algebraic alternative to Tartaglia-Cardano solution of the cubic. Use it straightforwardly to compute approximate numerical solutions. Specializing the above geometric polynomial formula. We have a cubic polynomial which has formal power series representation given below. Right. Catalan of M2, M3 is the bi-tri array. Counts not only sub-Diagons with M2 triangles, M3 quadrilaterals, and no other kinds of faces, but also the number of full plane trees with exactly M2 binary nodes and M3 ternary nodes. This is nuts. It's awesome. Eisenstein's example, immediate corollary to one of the above, says the quintic equation has formal series solution, generalized. Oh my goodness.
I just wanted to let you know
inversion of series and Lagrange. Edge layering on S, face layering of S, and the geode factorization. Obvious question for investigation. What besides subdigons do hyper-Catalan numbers C sub m count? Can we give direct bijective correspondences between these different incarnations? Schutz and Wielden and Rhodes have found interesting other such structures. There are likely many more. How does the surprising connection with Euler's polytope formula manifest itself in these other situations? Pure mathematics formal power series give algebraic and combinatorially explicit alternatives to functions which cannot actually be concretely evaluated, such as nth root functions. Hence, they ought to assume a more central position. This is a solological way of removing many of the infinities which currently abound in mathematical landscape. Yeah. Simplifies it to now being an infinity inside an infinite sum, rather than an infinity inside of all of the random calculations that we have to do. Norman J. Wildberger is an ardent YouTuber. You don't say. Channel name appears to be Insights into Mathematics. At NJ Wildberger. Yep. So if you want to check out any of his stuff, that is his YouTube channel. So you should be able to get in there and check out any of the stuff that he teaches. No warning. Just threw me into ads. Cool. So we'll be back in 3 minutes. Be right back.
Somehow I woke up out in Beverly, fucked up, smelling like that bourbon, and I end up alone. I'm not certain. Yeah, the girls impolite in the club every night. That's how it goes when you Hollywood perfect. Hollywood perfect. That's how it goes when you Hollywood perfect. Hollywood perfect. Ain't got no place to call my own. Feels like I'm better off alone. So sad inside and hopeless. These Hollywood hoes never notice.
All right. So anybody who wants to read the actual paper, have the full DOI at T&F Online. And there you go. So anybody who wants to read that full article, that's where you can find it. That is absolutely bonkers to me.
Somehow I woke up out in Beverly, fucked up, smelling like bourbon, and I end up alone. I'm not certain. The girls impolite in the club every night. Somehow I woke up out in Beverly, fucked up, smelling like that bourbon, and I end up alone. I'm not certain. The girls impolite in the club every night. That's how it goes when you're Hollywood perfect. Hollywood perfect. Hollywood perfect. Hollywood perfect. That's how it goes when you Hollywood perfect.
All right. So if anybody has anything that you want to talk about, that you want to look at, please let me know. The GOtEL fundraising event started with a goal of $205,000, and they are currently at, across all people running this campaign, $121,658.26, and it is the 7th of May. They're running this the entire month. Oh my goodness. Alright, and furthermore, we're going to just run a Let's run some Eskrima, because I'm not going to have time this week. And maybe we'll throw in a Tai Chi one in there as well, because I probably need to practice that. Start with Tai Chi, in fact. So with my instructor, who is also my Eskrima instructor, he had started out as a Tai Chi student and then eventually learned both Tai Chi and Eskrima, and he's pretty amazing in both of them. Basically, you need to like learn how to move people when you're in Tai Chi, and you just don't move him. All right, so we start with raising the arms up, and once they get to about here, they sink back in, push out, and then push down, look left, step and make a ball. From here, we do what's called a ward off and step this way. So this is basically protecting the body against anything that's coming in from over here, and then also keeping a structure with the left hand. So this is more like, if I let this go, I could keep this up all day, but at the same time it doesn't really do much. So when we bring this in, it like solidifies the muscles on the back. And then we bring this a little bit further to the right, leave this right hand where it is and sink back a little bit. And then come back. And this is where I forget stuff. That's really frustrating. Right, come from here, sink back, come back this way, and then this comes down, comes back, push or press, and then we drop and lean the body in, come back, sink, stop, or sink back, push, and stop. And then from here, this is kind of the end of the form as I know it, but what we can do now is then repeat that last bit. So we go back to the ward off position like this, and then we come twist right, sink back, return, round press, push, and then return. Back to the ward off position, further outside of the line, sink back just a little, that was too far, whatever, it's fine. This comes back over, press, push, sink back. I really probably want to be able to do it on the left side as well with my left leading, but we haven't done literally any of that. Some of the other stuff that we do are just to do the ward off position and press against each other's forearms. So like forearm to forearm, and then just like hold that position. You engage the glutes and like most of your leg and stuff like that, and it just basically, you hold it here, and then you bring up the left hand to keep your frame in the ward off, and then you just stand here, and when you press against each other, it causes you to start building up muscle, not just in, and it's a completely different kind of muscle and a completely different place than any other muscle you've ever built. So it hurts. So you just kind of like sink into this particular position, locking all of this up. And then when you're pressing against the other person, like you don't go anywhere. It's basically a standoff between two statues. And then at that point, we also did a bunch of just playing around and stuff like that, where you go forearm to forearm, and then allow... The idea is that you're going to push the other person in sort of a circular motion, then come back out. I'm holding his elbow and his wrist and kind of like guiding each other in this kind of circular motion as we go around. And at some point, one of us is going to slip or make a move or do something a little weird, and then suddenly all you need to do is take a quick grab or a quick shove, and the other person's off balance, and game over. But it's also very interesting to learn that, because as you do it, you start getting better at sensing each other's tactics, and so learning each other's tactics then is going to like make you better at fighting that one person. So then you have to try like a whole bunch of other people, and get some new blood into the system there, and try and work with other people to try some different tactics and have them try different tactics on you. It's very fascinating. All right, and then some Eskrima, as always. Not literally always, but you know. So, warm up the muscles. Try not to get tense, because otherwise, well, if you've got 500-gram sticks like these, stuff goes south real fast. The 120-gram trainers, generally speaking, are pretty good for, first learning and making sure that your technique is correct. The 250 polycarbonate ones I have are really great because they're practically indestructible. They're a bit heavier. They're a bit longer, which is really weird. But that also helps you not get too complacent. Right? You do something different, things are going to be a bit different. And then we get rid of the socks, because why would you want socks while you're doing martial arts? Grip the floor way easier. Right, so our standard sticks to heaven is that we have 2 machetes. Eskrima is a Filipino martial art, which was originally used with machetes in order to protect oneself from the rampaging mafiosos, Filipino mafiosos. During the time, there were some organized crime syndicates which were conspiring to take people's money. Nothing really surprising there. Alright, go with the music. Ugh. Oops. Right, so if we go a bit faster, this is from the shoulder, a 45-degree angle strike return to the other shoulder, a 45-degree angle upward strike coming from the bottom. We then twist our left hand around and swap left and right, and in doing so do another 45-degree angle strike on the right hand side, and then return that to our hip. And then same on the other side, left side, 45-degree angle strike downward, return to the other shoulder, 45-degree angle strike upward, twist, swap, 45-degree angle strike down, and then return. So and like I said, with these things, they're big, they're heavy, they tire me out pretty quickly. But we're building muscle, we're getting it figured out. And these aren't real machetes, so they won't cut me. From here, there's also several things that we had learned these past couple of weeks. So one of which was we were taking from here. We had a fan block, which generally started as out, like a backhand to a front hand, and then into a strike down to the opposite side. These past couple of weeks we learned a quick one, which was just do the forehand strike, which is very cheeky and oftentimes a surprise because they're usually expecting the offhand block first or the reverse. This one's just straight into that, and if you can come off the shoulder, go right above your head and immediately strike into their face, then they're typically not expecting that. The left hand side then goes slash around. It's pretty much straight across, and then this arm goes up, and then this uses the I think it's called a kadlik, where we do that comma sort of shaped strike back down over here. And then we're in this position, we're primed to immediately strike with the forehand across kadlik. And then we can keep doing this as long as we want. Good evening, patient T. So this was Eskrima, which is a Filipino martial art used against mostly Filipino mafia back in the day. But the Spanish colonizers that came over were none too happy that all these people in the Philippines were like training martial arts with machetes. So they were like, hey, this is a little scary. I don't know if I like this very much. So they banned martial arts, and in particular the usage of machetes other than for working in the fields. And so the Filipinos were like, okay, and then they just used sticks to train. And then they could actually hit each other with sticks too. Lightly, you know. Anybody who's done martial arts training, you know, you've been hit by something before. All right. So we were talking about a new discovery, which was that using Catalan numbers, which were the numbers that basically correspond to the number of the number of different partitions that can be made. So in this particular case, right, the number of partitions that can be made are going to be, this is a little obvious, but 3, 4, 5. Probably should have copied this. 6. 7. And I think 8. So we don't do anything. That should be the number of non-overlapping partitions. No. No, there's more. How many more? Oh, cool. Dean Rubine, one of the guys who is co-author on this paper, is a volunteer of the Math Counts co-coach at Oyster River Middle School in Durham, New Hampshire. I actually did my student teaching at Oyster River, I think. Oyster River? Yeah. I think mine was at the high school, but still. Anyway, we were looking at this and saying that the Catalan numbers, here we go. 0, 1, 2, 3. Maybe I went about this the opposite way that I was supposed to. There we go. Zero, 1, 2, 3. It's supposed to be 5. Interesting. I disagree. There are more. Okay, so 3, right, for 3 points, that's going to be 6 factorial over 4 factorial, 3 factorial. Alright, so 6, 5 over 6. There should only be 5. Okay, so what did I do? Oh, is that it? Is it just those? It might be. The implication here is that it's being partitioned so that those are going to be like that. Right, so we can either do a null partition, an all partition, or then split into 2 groups. And those 2 groups in this particular case are going to be of 2 and 1. Given that there are only 3 things, those are the only possibilities. Okay, so this means that C3 is going to be equal to 5. So anyway, who's it? these co-authors found that if they use Catalan numbers, they can actually solve not just like like a quadratic equation. They found out that you can actually use this method to solve any polynomial equation of any degree, going all the way up. So, according to Galois, as well as many other mathematicians prior to the 1850s-ish, they were trying to figure out how to get general solutions for higher degree polynomials, and they were utterly failing to get a 5th degree polynomial. The issue was really they were trying to look at ways in which to isolate one of the terms and then take like a big root of that term. So, you know, get the 5th degree polynomial term by itself and then move the 5th root to the other side, and then break up all the other stuff inside. Instead of being like x to the 4th, x to the 3rd, x squared, etc., there would be some way to break them up so that you could take the x to the 3rd term now, or x to the 4th term now, and then break that up into a 4th root with a bunch of other stuff. And then the x to the 3rds would all be broken up into cube roots of some kind. And so it would get really big, really fast, and really ugly. Évariste Galois, a French mathematician, came up with Galois theory, where basically it was proven that it was impossible to then solve the 5th degree polynomial using that method. So, good job, Galois. You ruined it. So, these people ended up finding out that you don't need to be limited to Galois theory. So we can, in fact, use combinatorics instead in order to figure out how to solve these higher degree polynomials. It's utterly bonkers. And I can't understand probably even half the article. But you know what? It's good stuff. So if you want to check any of that, check the article over that way or down that way or wherever it is on your particular on your particular browser window, what have you, or app. But yeah, check it out. Read it best you can. I can only understand a certain percentage of it, so don't feel bad. And then they built a new structure, which are called geodes. So you can build geodes, which are these Catalan number influenced mathematical structures, which have certain properties, and that eventually help you find the solutions to these particular higher degree polynomials. It's pretty great. So, if anybody has any actual questions, let me know. We can work on some problems. We were just talking how some researchers apparently cracked how to solve polynomials generally. And not just one family of them. No, like literally all of them. That's pretty amazing. Okay. So anybody who doesn't know me, my name is Obi-Wan Pez. This is N Simplex Pachinko, and my specialties are mathematical pedagogy, specifically going basically from basic math and pre-calculus, which is the one that I was running for many years, all the way up through Calc 1 differential equations. Calc 1 I've done many, many times. Calc 2 I've done a bunch in the last few years. And differential equations is my favorite, I think. So we might pop into differential equations would be cool. All right. Got a particular section you want to talk about? Let's see if we have that book. I literally just had the book open, like 2 hours ago. There it is. Non-homogeneous linear systems? Alrighty. Oh, what do you know? It's right there. Shove that over there. Okay. So, y prime is equal to, we have a series, or system of equations, which is going to get us the overall differential equation, that when we take the derivative of y, we're going to end up with 1x plus 2y, or yeah, doesn't matter, that's fine, plus 2e to the 4t, and we also have 2x plus 1y plus e to the 4t. I should really do this out, right? This is going to end up being y1. I really need to keep the same stuff. X prime, y prime, and then we'll split this and just have them be two separate equations. Alright, this is a system of linear equations. We can see that they are differential equations because they have differentials in them. They are linear because as we look across, there are no terms which have an x that is being squared or taking the natural log of it or exponential or any of that stuff. Linear systems in normal form. We may call it something else. How do we get normal form? Systems in normal form. Da, 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 da.
Always on the lookout for new tunes?
Okay, so
Catalog of millions
that's just y prime is equal to some function of both x and y, which,
Tap the banner to learn more.
if that's the same definition that you're using, then that is what we have here. So because we have a system of equations, then we're using just two separate ones. Or, oh, do you mean not including function of t? Which would just be homogeneous, but... Okay, yeah. Nah, that's fine. So, the good news is that, like, even if you didn't want the function of t in here, the e to the 4t stuff, we're going to have to go through the null space solution in order to get that general solution in the first place. So we'll worry about it on the way. Okay, so what we've got going on here is that we've got a, well, we can rewrite it as a matrix system. So instead of just x prime, y prime, you know, all this stuff going across as like separate pieces, we can say, okay, this is now a matrix where we can now take our coefficients 1, 2, 2, 1 and multiply them by the vector xy. Oops. That is the vector xy prime, or the derivative of the vector xy, is equal to, here again, 1, 2, 2, 1 times the vector xy plus vector 2e to the 4t e to the 4t. Okay. So one way to think of this is thinking of this as if it were a like harmonic system. So something like a spring mass system. Or if you think of like a predator-prey model in population dynamics, right? There is a natural harmonic frequency to how all of this stuff works. So our null space solution is going to be, what is the natural resonant frequency of the situation that's going on here? So the way to figure this out is we look at our A vector, or A matrix, and we say, okay, let's subtract from it. Yeah, there's a better way to explain it first. Right, what we want is to say that we have what are called eigenvectors, which are going to be our not necessarily even solution, but these are our steady state vectors. So if we find ourselves on one of the eigenvectors, what's going to happen is that we are going to go directly along that vector and nothing else. We cannot do anything else. So typically what's going to happen is if you're on one of the eigenvectors, you are either going directly away from the origin or you're going directly to the origin. Nothing else. Right? So if you find yourself on an eigenvector, you are going one of two ways. Directly in or directly away from the origin. That's it. The eigenvalues are going to tell you how quickly that's going to happen and whether it's in or out. Right, so your eigenvalues are going to determine the rate at which each of the eigenvectors will act upon the particle that's being dropped into the slope field, if you want to use that. If you have a negative eigenvalue value, then it's going to be coming inward, and if it's positive, it's going outward. If it's a small number, then that particular eigenvector doesn't cause any action to happen very quickly, and if it's a very large number, then that eigenvector is going to be supremely involved in moving that particle. It does actually matter relative to the other ones what those numbers are compared to each other. So if they have a ratio of approximately 1, then they're going to have approximately equal influence over the particles that are being dropped into the slope field. Or negative 1. If one of them is really big and one of them is really small, then the one that is much bigger will have much more influence over the behavior of what's going on. Hey, Jay McKellis, how's it going? Okay, so how do we figure that out? Well, this is the case when A times our, I guess, A times our y vector is equal to just a number times our y vector. Right, so the eigenvectors occur when the motion that is happening, right, A times y, our position, A is the transformation that goes from one step to the next. It's, differential equation. So if we're going directly along that vector and that vector only, then we must be on one of the eigenvectors. So technically, right, we drop the E for eigenvector. Sure, why not? Doesn't matter. Drop that in there and say, this is what we're trying to find. So what vectors are going to be influencing this particular transformation? And again, we're looking for the natural harmonic frequency. So what's it going to be for this particular system? Well, all that matters is this stuff, right? Just that A. So what we want now is to say, okay, let A times y sub e minus lambda times y sub e be equal to a zero vector, or yes, a zero vector. Right, when we subtract this thing over there, we're going to end up having a zero there, but it has to be of the same size as the other stuff. So it's going to end up being a vector. For this, we can factor out on the right-hand side the vector y sub e, our eigenvectors, but on the inside, now we have to worry about, well, what size are these things? Lambda is just a constant. So like you can't subtract a constant from a matrix. Doesn't really work. A is a 2 by 2 matrix. So we have to have a 2 by 2 matrix. If lambda is just a constant, then we can have an identity matrix that is of the same size, 2 by 2, which multiplies that particular lambda, which then allows us to receive the appropriately sized stuff. And the zero vector is also going to be a 2 by 2. Nope. Sorry. Right, this is a 2 by 1. When we multiply a 2 by 2 by a 2 by 1, the middle numbers have to agree. The outside numbers are going to give us the final size. Okay. So what does that get us? Well, this says now that we need a zero vector. So the only way that we can multiply two things together and get a zero vector is if, one, y sub e is 0, 0. That's super boring. Right? Eigenvectors being equal to a zero vector is a trivial solution. You learned on a number line, filled in dot and an empty one have two different meanings. Yes. Two-step inequalities currently. Nice. Patient, yeah. So the way that our matrices have to work, right, is that we know A is a 2 by 2, and we know Y is going to be a 2 by 1. Those were the same. It's based on your coordinate system, right? How many coordinates do you have? It's a vector, so it's by 1. And then we just say, in this case, we just need an x coordinate and a y coordinate, so it's going to be a 2 by 1. 2 by 1. And if we multiply them together, 2 by 2 by a 2 by 1, middle numbers, again, have to be of the same size, otherwise you can't multiply them. And then the solution is going to end up being the outer numbers, which is a handy little hint, but you don't need to do that, right? If you've got a 3 by 5 by a 5 by 7, right, if you want to multiply these things together, I'm going to regret that. Right? If you want to multiply these together, then you're going to have to multiply each of the rows by each of the columns, and they have to match, right? So A11 and B11 are going to get multiplied. A, first row, second column, and B, second row, first column are going to get multiplied together, etc. So they have to match up. If they don't, you're going to have a problem, right? You're going to have a mismatch in the dimensions, and then those things aren't going to be able to multiply because you're going to have extra terms somewhere. Yeah. Okay, so this is a zero product property again. We talked about this in context of like pre-calc stuff. So we have a multiplication that we've got between two terms. The only way that we can get a 0 from multiplication is if at least one of those things is 0. So either the eigenvector is 0, in which case it's trivial, we don't care, it's too easy, or all that other stuff has to get us a 0 vector. So all of this, a minus lambda I, needs to be equal to 0. And again, 0 vector. How do we then make this a little bit nicer? Like, how can we let it be equal to just literally 0, the number 0? We need a number to come out of our matrices. How do we get numbers out of matrices? Well, look at the size of them. Right? The size of a particular matrix is dependent upon its determinant. I don't mean a literal size. I just mean like the bits that are coming out of it. All the individual terms are going to need to, we're going to need to make them all work and get a size of the matrix. This is really also a double check to make sure that it's not singular, right? If it is a singular matrix, if our determinant is equal to 0 just by itself, A, then trying to do this transformation is going to be kind of null and void in the first place. So we need lambda values out of this, which are not 0. Right? Otherwise, it's just going to be pointless. So, how do we do this? Well, we go back up to the top and we say that we want the determinant of the matrix A, which was 1, 2, 2, 1. Its determinant is equal to 0 when we take our identity matrix, and if you remember, identity looks like 1 with a bunch of zeros, except along the diagonal, where they're all 1. Right? Your main diagonal is 1s, everything else is 0s across the entire matrix. Once you got that, that's our identity matrix. Multiplied by lambda means that all along our diagonal, all of those terms are now lambda. Everything else, everywhere else in the matrix is 0. So when we subtract them, you have to subtract the things that are in exactly the same spaces in each of the matrices, which means that we take A, 1, 2, 2, 1, and then we subtract lambda from the main diagonal only. Everything else is minus 0. Okay. And then how do we do determinants? Well, we're going to multiply the main diagonal. So this is going to be 1 minus lambda times 1 minus lambda. And then subtract the product of the off diagonal. So that's that, yeah. Off diagonal being 2 times 2. Again, still has to be equal to 0. So here, now we've got a polynomial. So this is going to be 1 minus 2 lambda plus lambda squared minus 4 equals 0. And then we're going to move this stuff around a little bit, and we get lambda squared minus 2 lambda minus 3 equals 0. That's kind of nice. Right, looking for factors of 3 that break up into 2 factors, the sum of whom is -2, and they have to have an opposite sign. So that says that the larger number needs to be negative. Right, we only have 1 and 3 because this is -3 is our number. The larger number must be negative because our sum is negative. And they must have opposite signs, and of course we're in adds. Alright, we'll sort of hang on here a minute. If anybody is outside of... That's not what I want. Rawr. Righto. If anybody is still able to hear me, thank you very much for coming. We are raising money for GOtEL, which is Game On to End Lupus. Lupus is an autoimmune disease which can hit literally anybody at any time. There are factors which appear to be genetic and factors which appear to be environmental. And more or less what happens is the autoimmune disorder gets your immune system to start attacking systems within your body and causes them to start taking damage from all of your immune system making antibodies to fight yourself, to fight your own body. Lupus sucks. I don't actually know personally anybody who has it, but I do have several friends here several friends here on Twitch who have it. So the people who are running the GOtEL fundraiser are at 8BitD, Coco Confession, and Elbel, who 8BitD and Coco Confession, or D and Coco, have received their diagnoses and have been working toward getting something, trying to find some sort of medication that's going to minimize the autoimmune disorder's damaging effects. Ellie, our third person up there, is still waiting for, I believe, an official diagnosis, but like it's probably that. It's probably lupus. Because one of the other problems with lupus is you have to eliminate pretty much everything else before the doctor will resign themselves to saying, yeah, it's probably lupus. Just because if it turns out that what you have is not lupus and it's something else, some of the other medications that do treat lupus can be pretty damaging in a completely different direction. So we are raising money to help Game On to End Lupus with the Lupus Foundation of America. And if anybody is interested, the QR code's up there. I've got a link right in chat. I have also added a few interesting punishments if you would like to donate money to cause me pain. So, and if you would rather donate on any of their streams, feel free. Yeah. So, lupus is an autoimmune disorder, and it can affect literally anyone at any time. There are seemingly some effects or some causes which are genetic and some which are environmental. They tend to also, or most people with lupus tend to be women or have higher estrogen amounts. So there's some connection there, probably in the environmental section. And again, some genetic factors somewhere that people are trying to figure it out. Unfortunately, the National Science Foundation had a bunch of its budget cut, so yay. We are raising money for the Lupus Foundation of America, and that is not just me, not just these three wonderful people who are linked in chat, but there are approximately 160 of us who are going all together to try and raise $205,000. This is not out of nowhere, right? This is they've had successful LFA fundraisers every single year for the past 3 or 4 years, something like that. And they started at like low numbers and they just kept getting higher and higher. It's been really amazing. And D especially had a $30,000 goal, which I believe she already hit. It is the 8th of May, and we're doing this all month. So we're looking at if you're at all interested in continuing the goals, pushing everybody else's goals that are out there, or meeting some little peon streamer like me who has a little bitty goal, that'd be awesome. But no pressure. If you need the money for literally anything else, I completely understand. Academy of Useless Ideas, good evening and welcome everybody. Raiding on in. I don't think I have a command for that. No, okay. Worth a shot. Yeah, Walking Stick Library. It hits... I think D said there are 8 million Americans with lupus at give or take any time. And it comes and goes in waves. When people are having flares, that's kind of like when they need to get their particular... get the diagnoses done, but unfortunately there's also like wait times for diagnoses. You know, oh no, we don't have an appointment until like next week. Well, great, but not gonna, you know, I'm not gonna have a flare, or a flare might be over by next week. As I was saying, I personally do not have lupus. I don't personally know anybody with lupus, but I do have several streamer friends and other chat friends across many other streams and platforms who do, and it is insidious and terrible and very painful, and quite frankly I would like it to go away. So if we can do anything to help, that'd be awesome. If not, don't worry about it. Like I said, it'd just be cool. Okay. So, going back to what I was saying earlier, this is something that I did with my pre-calc students whenever we got to factorizing polynomials, right? If you're looking at quadratics, first of all, then what we want to look at is that our middle number, the sign of the middle number, is what we get when we add the two things together. Well, if we add two things and get a negative number, that means that the bigger of the two of them needs to be negative. Because we've only got one other number, right? And then that smaller number is going to get added. It's got to be negative. Hey, Super Henrik, how's it going? So that's why we say our 3 over here is going to be negative. And then we say here, this is what happens when we multiply the two numbers together. We get opposite signs. When do we get opposite signs? Nope. When do we get a product that is negative? That's when we have opposite signs that get multiplied together. So these have to have opposite signs. Since the bigger one is positive, the smaller one no. Since the bigger one is negative, the smaller one must be positive. So that's how we're going to do that. We get those two. This is telling us that we're going to get lambda. Okay. I'm going to be a pain in the rear. So when we do the AC method in like pre-calc stuff, then this is usually how we do it. So this is going to be lambda squared minus 3 lambda plus 1 lambda minus 3 is equal to 0. And then factor by grouping. So the first two have a lambda in common and then lambda minus 3. And then plus 1 times lambda minus 3 equals 0. And then factor lambda minus 3, lambda plus 1. No, I don't do this in my differential equations class, except to tell my students that this is a very convenient way to think about it if you haven't thought of it like this yet. And then here, lambda is equal to 3, and lambda is equal to negative 1. Or lambda is equal to negative 1. Yes, eigenvalues. Can't you just really remember 3 is 3? In theory? Which part do you mean? Alright, so when we do this, this says that we now have 2 eigenvalues, 3 and negative 1. Yeah, but I try to get them to realize that, like, oh, the negative 3, or the 3 has to be the negative 1, because here we've got a negative 2 in the middle, and so the bigger number has to be negative. And then, of course, when we start getting into like much more complicated examples, I want them to remember these easy things so that it's a little less worrisome for them. They don't get tripped up on misconceptions. Don't know what that was. Seems I may have had a coffee hole in my coffee, but guess I can understand. See it through before you figure it. Yeah. And I'm also offering a one-size-fits-all sort of thing, so because I'm doing that, I need to, like, make sure that it's covering as many possible misconceptions as I can, as quickly as I can. And that's hard, but it takes time. If anybody has not followed Academy of Useless Ideas, please go check them out. Naturally, we're working on math tonight. And if you, you know, need to raid and run and what have you, feel free to do that as well. Word problems, yep. Okay, so when we were looking at this, we had lambda equals 3 would then get us a particular eigenvector. So we had 1 minus lambda, so minus 3, 2, 2, 1 minus lambda, again, make that 3. And we said that what was going to happen, hard reset, yeah. What we set up above was that a minus lambda I needed to be equal to our 0 vector. So each of the terms, each of the sets of terms need to be equal. And then when we subtract them like we do here, we should get a 0 in both places. So what we're doing is we're going to create an augmented matrix. Which, what it really means is that we've got A minus lambda I all multiplied by our xy vector is going to be equal to 0, 0. But it's always going to be multiplied by this xy vector every single time we do this. So basically we just skip the xy vector and make this augmented bar go in the middle and say that's really what this means, don't worry about it. We've got the xy, we've got the equality sign. We'll just make sure that we've got a minus lambda I over here and zeros over here. That's what really matters. So remember, the values lambda were our eigenvalues. These were going to tell us how quickly, relative to each other, the particles are going to be responding to those eigenvector directions, or the eigenvectors will impart a certain amount of force in their particular direction. So what is that force? Again, comparatively, if your eigenvalues are close to each other, then they're going to be approximately equal in terms of their influence. If they're really far apart from each other, then they're going to have very different amounts of influence compared to each other. So now what we're trying to do is find the eigenvectors associated with those eigenvalues, respectively, because each one eigenvector has one eigenvalue associated with it. So here we pick lambda equals 3. We're going to do both of them, but pick lambda equals 3 in this case, and then we say, all right, what's the eigenvector associated with that value? So this is negative 2, 2 augmented 0, and 2, negative 2 augmented with 0. We're going to do matrix operations. I'm going to take row 1, and I'm going to multiply it by negative 1/2, and then put it back into row 1. Because I want to get a 1 in the pivot position, top left corner. It's not like it really matters a huge amount, but like this makes it a bit easier. And then in order to clear out the pivot row or pivot position in the second row, I need to now add, right, row 1 plus row 2 and store that back into row 2. And wouldn't you know it, this is going to get us a 1, a negative 1 augmented with 0, and this is going to get us a 0 and a 0 augmented with 0. Oh shucks, whatever happened? So what does this mean? Right, if we go back to our algebra 2 or algebra 1, way back in the beginning of high school or further or closer, whatever. I'm not judging. Remember that when we have a system that eliminates one of the rows entirely and we get 0 equals 0, this is a dependent system. There are an infinite number of solutions, meaning that there is not one particular place. Yes. There is not one particular place. Thank you very much for the follow. There is not one particular place where these vectors exist, right? It's not like a single point out in space. It's a vector. It's going to be along a line. So actually, it makes complete sense why we should get a line, right? In this case, we get x minus y is equal to 0. X equals y. It's a line. Right? The line y equals x, 45-degree angle, going all the way through our coordinate axes. This is one of our vectors. And again, it had an associated value of 3. So the real kernel 1. So we're doing all the way back at the top. We're doing linear differential equations. Sorry, systems of linear differential equations. And so we're looking at trying to find eigenvalues and eigenvectors. And this is what we found. So our R value, the radius of this particular vector, is 3, and it's going in that direction. So this ends up being, do I do discrete? Can. What would you like? Thank you for the follow. So these are going to be like 3 over root 2, comma 3 over root 2. In order to have a radius of 3. Alright, that's our x and y components. And then we need to find out our second eigenvector. We do 1 minus negative 1, 2, augmented with 0, 2, 1 minus negative 1, augmented with 0, and oh goodness, wouldn't you know, we get 2, 2, augmented 0 in both lines. Oh shucks, whatever's going to happen. Right, row 1 minus row 2, store to row 2, and then row 1 times 1/2 back to row 1. Convert prenex form and apply Skolem. I have no idea what that is, but I can look it up. Okay, so 1, 1 augmented 0 and 0, 0 augmented 0. Again, same deal. It's just ever so slightly different. Thank you very much for the hydrate. This says that x plus y is going to be equal to 0, and therefore y equals negative x, with a lambda of negative 1. So what that means is now we have a vector which is going to come inward. Along that particular along that particular setup there. Now, this also means that it's going to go in both directions. Like this. So then the vector field for like the rest of everything else in space, it's going to look something roughly speaking like this. Let's see. The one on our y equals x also has like 3 times the influence of the other stuff. So this is all going to come in, but then it's going to get sucked out this way pretty quickly.
Over 20 years as hearing experts too, even though we're called Specsavers. Book a free hearing.
So our vector field is going to look something roughly speaking like this. We could find the actual values that we would get in many different cases, but this is what we see. Okay, so also the way that this works is that now we're going to get a general solution, right? xy is going to be equal to. We're going to get a linear factor, or a linear combination of those vectors that we found up there with the appropriate e to the, hang on, our fundamental set of solutions is going to be eigenvector 1 times e to the lambda 1 t, and eigenvector 2 times e to the lambda 2 t. Now when we get a fundamental set of solutions, we can then say that the overall solution is going to be the linear combination of those two things. Okay, so our vector that we had, there's multiple different ways that we can make this work, but nonetheless. We said that x minus y is equal to 0. We could have also said instead that we got let x be t. There's a bunch of different ways to do it, but let x equal a dummy variable t, and therefore we've got t minus y equals 0. So y is also t. And then we take this and we combine it, or we just take that one, combine it, and we say that our eigenvector associated with eigenvalue 3 is going to be equal to 1, 1. Right, our x and our y coordinates were equal to each other. They were going in the same directions at the same time, all that good stuff. And then likewise with this one, we get that our eigenvector associated with -1 is going to end up being... now here's the thing. This could be either 1, -1 or -1, 1. It doesn't matter, because what we're going to do is we're going to have a linear combination. So we're going to have a C1 in front of all of it, and then all that this does, if you change it from 1, -1 to -1, 1, you've just changed the sign of C1. That's it. So it's self-correcting. You don't have to worry about it. So 1, 1 was with 3t plus C2, 1, -1, e to the -t. Right, so this is our homogeneous solution. And then we're going to have to find the non-homogeneous portion of this, and we'll come back to that in just a couple of minutes. Triple integrals and cylindrical coordinates. I mean, I can. So, do something like this. Looking at symbols and numbers you don't quite understand. Yeah, there's a lot of Greek symbols that we use in differential equations. This particular squiggly is called xi, and I'm not doing it justice when I write it. It actually should look like that, I think, more or less. I just kind of go blah, 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 and then make it work. Weren't expecting the solution to look like that. Yeah. If it was XYZ, so if you were working in 3 dimensions, then yeah, you would have 3 terms, and each of the vectors would have an XYZ. Hey Fizzbuzz, how's it going? Oh, alright, fine. We'll sit up properly. You don't like me draped over my armchair? Alright, so if we do z is equal to, I don't know, just friggin' 1 minus 3xy or something like that. This is probably going to be horrible. But, you know what? It'll work. And z is going to go from, let's do 0 to 4. That's not going to work, is it? Hang on. Alright, well from surface z equals 1 minus 3xy. It is a hyperbolic paraboloid. Not gonna graph it for me though? Man. Yeah, there we go. Well, that's why it's a bonus question, right? This is probably not going to work. Maybe not z is equal to. Maybe this is just like f of xy. Or xyz, I don't know. We'll see. So we want a triple integral 1 minus 3xy. Okay. What's like the least worst thing? Okay, so like r equals cosine theta is going to be x minus a half squared plus just y squared is equal to radius of a half. So 1/4. So y is equal to the square root of 1/4 minus parentheses x minus a half parentheses squared. This is maybe a terrible idea to attempt something like this just blind, like making up an example. It's one of the problems that happens all the time when I was teaching. Usually Calc 2. But I can completely understand. So like, if we wanted to put z out on the outside, x here, y here, y is going to go from negative to positive of the exact same thing. It's symmetric, so we should be able to go from 0 to the positive square root and then multiply it by 2 on the outside. Right, 1/4 minus parentheses x minus a half squared. There's something wrong. I think maybe this was going to go from like 0 to 1 minus 3xy. In which case, z should probably come first. Then y, then x. This would shift this stuff. To here. Our z would go from 0 to 1 minus 3xy. And our x would go from 0 to 1. Right, this would mean like we don't have a density that's going to mess around with any of the other stuff. So dz, dy, dx in order. So this means that we're going to get x and y on 1 minus 3xy minus 0, so don't worry about it. Dy, dx. This is going to get us 2 times x integral. This is going to be y minus 3 halves x y squared dx. We still need to evaluate y from 0 to that particular square root, which is gross. Alright, a quarter minus parentheses x minus a half squared. That is going to be a I was going to think inverse trig, but that doesn't work. We're going to probably have to use a trig substitution to make that work. Minus 3 halves x times square root squared. So this is going to be 1/4 minus parentheses x minus a half squared and dx. Okay, we're going from 0 to 1. This is going to be twice x going from 0 to 1 on a square root 1/4 minus parentheses x minus a half squared dx minus 3 integral x goes from 0 to 1 of 1/4 minus parentheses x minus a half squared dx. Alright, so this 2 is going to multiply by that half. That's going to clear. And then we get a minus 3 times the x. Definitely works. Makes 100% sense. Don't know what anybody's talking about. Okay, minus subtracted from 1/4 x. Okay, this is a polynomial. Super easy. No worries. Less nice. If x is 1/2 sine, so 1 minus sine squared makes a cosine squared? Sure. 1/2 sine of the thing plus 1/2. Right, that'll add the half to the negative 1/2 on the inside, it'll go away. And then it squares the 1/2 sine, and it becomes 1/4 sine squared. Yeah. Yep. And then the 1/4 factor out from both terms, we get a 1 minus sine squared is going to make a cosine squared by itself. Makes it nice. Okay, then dx is going to be equal to 1/2 cosine theta, d theta. So, this is going to make 2 integral on theta. Worry about that in a minute. Right, 1/4 minus 1/4 cosine squared theta. Dx is 1/2 cosine theta d theta. Oops, that's a sine squared. So give me a 2. Okay, square root 1/4 square root 1 minus sine squared theta times 1/2 cosine theta d theta. This 2 and 1/2 are going to get multiplied out, and then the square root of 1/4 is going to be 1/2 times the integral of on theta of square root of cosine squared theta is just going to be cosine of theta times cosine of theta d theta. Oh, that's inconvenient. That's all right. Cosine squared theta d theta. Reduction of power. It's going to be the integral on theta of cosine squared. Okay, so this is 2 cosine squared theta plus 1. No, minus 1 equals cosine of 2 theta. Therefore, we flip all this stuff around. This is going to make 1 plus cosine 2 theta all over 2 is equal to cosine squared theta. So 1 plus cosine 2 theta all over 2 d theta. That's going to be 1/4 integral on theta 1 plus cosine 2 theta d theta. 1/4 times, this is going to be theta, plus sine of 2 theta, then the derivative of the inside 2 theta is going to be 2 d theta. So we need a 2 on the inside of that portion, which means on that portion we also need a 1/2 to balance it out. Probably shouldn't have moved the other one, but whatever, it's fine. Actually, it didn't matter, right? We need an extra half on that one. If we go from 0 to 1 on x, then we can translate that here to 0 to pi over 2 on theta. Which gets us to 0 and pi, so the sign goes away entirely. It's pretty nice. Alright, so all this stuff is 0. And then here we should get just pi over 8 plus the polynomial that we had up here. Okay, so then this is going to be a -3 times 1/4 x is going to end up being 1/8 x squared. This is going to be x squared minus 1x plus 1/4 all multiplied by x, negative x. So this is going to be a negative x to the third plus x squared minus 1/4 x. When we take the integral of those, this is going to become a minus 1/4 x to the fourth, a plus 1/3 x to the third, and a minus 1/8 x squared. Right, those terms end up subtracting out. X goes from 0 to 1. Zeros are going to drop out and be zeros, and then we just get the ones. So pi over 8 minus 3 times 1/4, and both are negative, so positive 3/4. 1 to the fourth is still 1, so that just stays where it is. And here, -3 times 1/3 is going to be a negative 1 x to the third, so that's going to be a minus 1. So pi over 8 minus 1/4. Next question. What sign does that have? That's going to be disastrous if this is a negative number. Probably not. No. This is approximately 0.1427. Alright, that's cubic units. Alright, good times. So most of the time when you have any form of cylindric, or if any form of coordinate system that is not obvious in terms of what you're doing here, what we're doing is first off look and see if there are any variables that have, if you solve it from one of the variables, does it have one or two other variables in it? Is there one that is obviously independent in this particular case? So x felt like we could have used independent variables. We could also have used y as our independent variable because this is a circle in the x and y directions, right? Like, who cares? We could use it. It doesn't matter. I chose to use x as the independent variable just because we could use the equation of a circle ever so slightly easier, but like it's fine. Probably could have done fine either way. Actually, you know what? This isn't even cylindrical coordinates. I screwed that up. Yep, that's not even cylindrical coordinates. That's just using a triple integral. Damn. Okay. So if we want cylindrical coordinates, we would want r equals cosine theta is our base, where theta goes from 0 to pi. And our height, right, capped by z equals 1 minus 3xy. Yeah. Okay. So cylindrical coordinates are using a literal cylinder in this case. We want to know what is the angle that we're going to sweep out in 360 degrees. In this case, we're going to do 0 to pi to get one full loop of that little circle. Right, so from 0, as we increase theta, let's see, r starts at 1. So radius of 1, we're going to start here at this part. And then as we increase, we're going increase theta, which is going to go up. Or backward in this plane. We're going to start decreasing our r value until we reach an r value of 0 at... right, pi over 2. We're all good. And then it goes negative in the second quadrant. So normally our theta is going to be up in the second quadrant, and it's getting us a negative r value that shoots us back down in the opposite direction. So we're down here now, from pi over 2 to pi. Once we reach pi, we're back where we started. If you go again to 2 pi, then you're just going to trace over the exact same circle. So this is unhelpful. We only need to go from 0 to pi, and that's just it. Okay, so if we do this, right, then we're going to want as our independent variable theta. See how this goes. We're going to want r we're going to want, right, z goes from 0 to, and this is the thing, either we can, well, we can't do it. We can't do it that way. So we need to get x and y in terms of r and theta. It's not going to be 3xy, right? We have to work that out. So if r equals cosine of theta, no. Y equals r sine theta. X equals r cosine theta. Z is equal to 1 minus 3 r squared sine theta cosine theta. We're on adds again. Right. One more minute. Okay. Thank you everybody for sticking around. So, the way that I'm seeing this is that we're going to use x is r cosine theta, y is r sine theta for any particular value that we're going to get. Our z is going to be based on the height limit anyway, is 1 minus 3xy. So the way that we're going to make this work is that we're going to say that z is going to go from 0 up to that particular limit, and we've changed x for r cosine theta and y for r sine theta. So combining these things together, we get z is going to go from 0 to 1 minus 3r squared sine theta cosine theta. It's okay. Not my favorite, but it'll work. R is going to go from 0 to cosine theta? Yeah. So from 0 out to whatever cosine theta is at that particular angle. And then theta is going to go from 0 to pi. Okay. So z is going to be integrated first. And we're just going to get z dr d theta. Now what is z? Because that matters for the other two integrals. Z is going to be 1 minus 3r squared sine theta cosine theta. dr dz. No, dr d theta. Alright, when we take the integral with respect to r, and we still have the integral with respect to theta, we're going to now have r minus 3r squared. Take the integral becomes r cubed. Sine, nope, not squared. Sine theta cosine theta. d theta. Okay, we need to evaluate r equals, this is going to go from 0 to cosine theta. So here we have the integral on theta. Cosine theta is going to be here minus 0, just 0, minus cosine to the 4th theta times sine theta minus 0 times all the rest of that stuff goes away. And now we've just got d theta. The first one is super simple. We just take the integral of a cosine, we get a sine. The second one, slightly harder, but it's not that bad. So here, if we let u be equal to cosine of theta, du is going to be equal to a negative sine theta d theta. We've got a negative, we've got a sine theta, we've got a d theta. Cool. So now we have cosine of u, nope. We have a u to the 4th du. So this is going to be 1/5 u to the 5th, which is going to be a plus, because we use the negative as a part of du. 1/5. U is the same as cosine of theta to the 5th power, evaluated from 0 to pi. Okay. Sine of theta is going to be 0 for both of these. 0 and pi. Plus 1/5. Cosine to the 5th of pi minus 1/5 cosine to the 5th of 0. Oh dear. That's not a number I want. Oh. Did I screw up somewhere? Probably yes. What did I get in the other case? Pi over 8 minus a quarter. Oh no. I screwed up something. Oh. Oh. Right. No. Never mind. I mean, it's still not going to get us pi no matter what we do. Well, that's annoying. So we got like 2/5. Granted, technically it's negative. Technically. So that shouldn't have happened. We should have gotten a positive number. And we probably should have gotten some pi in here somewhere, but that's weird. Okay, area, let's do this. Wolfram, do me a favor. Find the area under z equals 1 minus 3xy bounded by r equals cosine t, it's fine, and t is going to go between 0 and pi. You kidding me? Volume. Above the circle. I am disgusted. Aye. Triple U. Uh-oh. So I did XYZ as the original triple integral, which got us a value of pi over 8 minus a quarter, or 0.1427. I am now getting a value of negative 2/5, or possibly positive 2/5, but nonetheless, those are not the same value. And I'm trying to figure out where I screwed up, but that is not particularly easy. Oh well. Alright, I think that's gonna probably do it though. So we'll head over to... Really? Gonna probably head over to one of our other math streamer friends. We got the tutor wizard who just got on. Linear algebra practice problems. Sounds pretty promising.
Hello, mate. Got any tips for the football? Your best bet is to head over to Bet Victor. They're giving new customers a terrific welcome offer. If you bet a minimum of £10, they'll give you £30 free bets. Oh, that's a steal of a deal. It's a good darn deal that'll make you squeal for real. Neil?
My name's not Neil.
I know, but it rhymed.
Listen to Harry and make your best bet on the football at Bet Victor. 18 plus, opt in and bet on any football marketing at odds of evens or greater. No cash out, 7-day expiry. Terms and conditions apply.
Sometimes you just want something a bit extra to satisfy your cravings.
Something creamy, full of flavour, something a bit...
Yazoo!
Yeah, try new Yazoo Inspirations. 2 delicious milkshakes in birthday cake or caramel blondie flavour.
And Dr. Gold is on. Doing a little arc or angle
Give your treat more taste with new Yazoo
of a circle given particular
This is an ad by BetterHelp.
restrictions.
75% of
Okay.
girls said they feel anxious or on edge. Many avoid
I think we're going to go over and see the tutor wizard.
staying
Going to do some linear algebra type stuff.
affects everyone.
So we'll see how they're doing.
10 years of experience matching people with the right therapist.
Thank you so much, everybody, for hanging out.
BetterHelp
We have here our other math streamer friends. We need to add people to this list, but nonetheless, this is approximately who we started with and have added to over the past year or so. Go and check them out. They do awesome work. And again, GOtEL, if anybody is interested in donating to end lupus, because we're trying to boost that boost this charity movement as much as possible and try to invest in getting people better and helping them do more awesome things in the world. Hopefully the disease will not hurt them super for much longer. So we'll see how things go. Anyway, I will see you all possibly tomorrow. Otherwise, that's going to be it for me for until next Tuesday. So, hope you all have a good weekend. My name is Obi-Wan Pez. This is N Simplex Pachinko. See y'all later.